In this video, we will discuss about basic electrical and electronics engineering, Unit 1, DC circuits, question bank solutions. Part B, analyze the VA relationship between RLC parameters. Resistance. The property of a material to restrict the flow of electrons is called resistance. It is denoted by R. The symbol of the resistor is as shown in figure. The unit of resistance is ohm. OHM. Ohm is defined as the resistance offered by the material when a current of 1 ampere flows between two terminals with 1 volt applied across it. According to Ohm's law, R equals to V by I. When current flows through any resistive material, heat is generated by the collision of the electrons with other atomic particles. The power absorbed by the resistor is given by P equals to Vi R, which is equals to IR into I, which is equals to I square R. Energy lost in a resistance in time t is given by W equals to integral 0 to t P into dt, which is equals to P into t, I square R into t, R V square by R into t, where V is the voltage in volts, R is the resistance in ohms, T is the time in seconds, and W is in joules. Inductance. A wire of certain length, when twisted into a coil, becomes a basic inductor. The property of a material by virtue of which opposes any change of magnitude or direction of electric current passing through the conductor. It is denoted by L. The symbol for the inductor is as shown in figure. The unit of inductance is henries and it is denoted by H. The inductance is 1 Henry when current through the coil changing at the rate of 1 ampere per second induces 1 volt across the coil. V equals to L di by dt. Hence, we can rewrite the above equation as I of t equals to 1 by L integral 0 to t V dt. The power absorbed by the inductor is P equals to Vi equals to Li into di by dt watts, and the energy stored by the inductor is W equals to integral of 0 to t P into dt. From this we can obtain integral 0 to t Li di by dt into dt. Dt will be cancelled, which is equals to Li square by 2 or half Li square. Capacitance. It is the capability of an element to store electric charge within it. A capacitor stores electric field being established by the two polarities of charges on the two electrodes of a capacitor. The property of material by virtue of which opposes any change of magnitude of voltage across the conductor. It is denoted by C. The symbol for capacitor is as shown in figure. The unit of capacitance is farad, denoted with F. By the definition, 1 farad is the amount of capacitance which 1 coulomb of charge is stored with 1 volt across the plates. Capacitor is have greater capacitance if it can store more charge per unit voltage, and the capacitance is given by C equals to Q by V. We can write the above equation in terms of current as I equals to C dV by dt, where since I equals to dq by dt. where V is the voltage across the capacitor and I is the current flowing through it, and the voltage V of t is given by 1 by C integral 0 to t I dt. The power absorbed by the capacitor is given by P equals to Vi, which is equals to Cv dV by dt. The energy stored by the capacitor is W equals to integral 0 to t P dt. Now you can obtain the expression energy stored by the capacitor equals to half Cv square. State and explain Kirchhoff laws. Kirchhoff laws. A German physicist Gustav Kirchhoff developed two laws enabling easier analysis of an interconnection of any number of circuit elements. Kirchhoff voltage law states that the algebraic sum of voltages and voltage drops around any closed path is 0, or in any closed path the sum of voltage drop is equal to sum of voltage sources. Considering the circuit in the figure, it is customary to take the direction of current I as indicated in the figure, that is, it leaves the positive terminal of the voltage source and enters into the negative terminal. As the current passes through the circuit, the sum of voltage drop around the loop is equal to the total voltage in the loop. Vs equals to V1 plus V2 plus V3. By using Ohm's law, we can find the voltage across each resistor as follows, where VR1, VR2 and VR3 are the voltages just across R1, R2 and R3 respectively. Finally, by applying KVL, V equals to VR1 plus VR2 plus VR3, which is equals to V equals to IR1 plus IR2 plus IR3. From the above equations, we can find the current delivered by the source is given by I equals to V by R1 plus R2 plus R3. Current law. Kirchhoff current law states that the algebraic sum of currents at any node or junction of a circuit is 0, or the sum of currents entering into any node is equal to sum of currents leaving that node. From the above diagram, the sum of currents entering any point or node or junction is equal to the sum of currents leaving from the point or node or junction. I1 plus I2 plus I4 plus I7 is equal to I3 plus I5 plus I6. If all the terms on the right side are brought over to the left side, their signs change to negative and 0 is left on the right side. That is I1 plus I2 plus I4 plus I7 minus I3 minus I5 minus I6 equals to 0. Explain about different types of energy sources. According to their terminal voltage current characteristics, electrical energy sources are categorized into ideal voltage sources and ideal current sources. Further, they can be divided into independent and dependent sources. Ideal voltage source. An ideal voltage source is a two-terminal element in which the voltage Vs is completely independent of the current Is through its terminals. The representation of ideal constant voltage source is as shown in figure A. If we observe the VA characteristics for an ideal voltage source is as shown in figure C. For any time, the value of the terminal voltage Vs is constant with respect to the value of current Is. Whenever Vs is 0, the voltage source is the same as that of short circuit. Voltage source need not have a constant magnitude. In many cases, the supplied voltage may be time dependent, like a sinusoidal wave represented as shown in figure B. In many practical voltage sources, the internal resistance is represented in series with the source as shown in figure below. In this, the voltage across the terminals falls as the current through it increases, is as shown in figure B. The terminal voltage Vt depends on the source current as shown in figure B, where Vt equals to Vs minus Is into R. Ideal current source. An ideal constant current source is a two-terminal element in which the current Is completely independent of voltage source Vs across its terminal. Like voltage sources, we can have current sources of constant magnitude is are sources whose current varies with time Is of t. The representation of ideal current source is as shown in figure A. If we observe the VA characteristic for an ideal current source, it is as shown in figure B. At any time, the value of current is constant with respect to the voltage across it. In many practical current sources, the resistance R is in parallel with a source Is, as shown in figure A. In this, the magnitude of current falls as the voltage across its terminal increases. VA characteristics is as shown in figure B. The terminal current Is is given by of t equals to Is minus Vs by R, where the R is the internal resistance of the ideal current source. In the case of dependent sources, the source voltage or current is not fixed but is dependent on the voltage or current existing at some other location in the circuit. Dependent or controlled voltage sources are of following type: voltage controlled voltage source, current controlled voltage source, voltage controlled current source, current controlled current source. These are represented in a circuit diagram of symbol as shown in figure, where A represents a controlled voltage source and B represents the controlled current source. Formulate the effective resistance between A and B using star to delta transformation. In the given circuit, resistors 3 ohms, 2 ohms and 6 ohms are connected like a star. 3 ohms, 2 ohms and 6 ohms are like a inverted Y shape or like a star connection. The 3 resistances like in a star connection can be converting into like a delta. These three resistances can be converting into like a delta, like where R1 is equals to 2 ohms, R2 equals to 3 ohms and R3 equals to 6 ohms. By using the formulas from star to delta, the formula for R12 is equals to R1 plus R2 plus R1 R2 by R3. By substituting, since the value of R1 is 2 and R2 is 3 and R1 is 2 and R2 is 3 and R1 2 into 3 divided by R3 is 6. By finding, you can obtain 2 plus 3 plus 1, which is equals to 6 ohms. Similarly, R23 is equals to R2 plus R3 plus R2 R3 by R1. R2 is 3 ohms and R3 is 6 ohms plus 3 into 6 by 2. Here this is 3 plus 6 plus 9, which is equals to 18 ohms, and R31, which is equals to 6 plus 2 plus 6 into 2 by 3, which is 6 plus 2 plus 4, which is equals to 12 ohms. Now we can redraw the circuit with new resistances in between. here is R12 is equals to 6 ohms and R23 is 18 ohms and R31 is 12 ohms. 6 ohms resistors, 6 ohms and 6 ohms are in parallel. Which is equals to 6 into 6 by 6 plus 6, which is equals to 3 ohms, and 18 ohms and 9 ohms are in parallel. 9 into 18 by 9 plus 18 equals to 6 ohms, and 12 ohm and 12 ohm are in parallel, which is equals to 12 into 12 by 12 plus 12, which is equals to 6 ohms. We can draw a new circuit with resistances, which is 3 ohms, 6 ohms and 6 ohms. We are asked to find out the resistance between A and B terminals. Here, by observing 6 ohms and 6 ohms are connecting in series. Therefore, 6 ohms and 6 ohms are connecting in series, which is equals to 12 ohms. 3 ohms and 12 ohms are in parallel. 3 into 12 by 3 plus 12, which is equals to 12 by 5. 12 by 5 is 2.4 ohms. Therefore, resistance between A and B terminals is 2.4 ohms. Find the current supplied by the source using nodal analysis. In this question, we have been asked to find out the current supplied by the source, which is nothing but current supplied by the 10 volts voltage source. In the given circuit, there are two nodes are there. Node 1 in between and node 2. Now here no need to consider another node at this 10 volts, because here this node voltage directly, which is nothing but 10 volts. Now here assuming a two nodes, node 1 and node 2. Now at node 1 we will assume a voltage V1, and node 2 we will assume a voltage V2. By applying node analysis, at node 1, V1 is the potential, V1 minus 10 by 2 ohms, and V1 minus V2 by 3 ohms is the resistance, and V1 minus 0 by 12, which is equals to 0. Here this ground is having a 0 potential. Now by separating V1 and here terms v1 by 2 plus minus 10 by 2 plus v1 by 3 minus v2 by 3 plus v1 by 12 equals to 0. Separating v1 and v2 terms, v1 into 1 by 2 plus 1 by 3 plus 1 by 12 minus v2 coefficient is v2 into 1 by 3 equals to 10 by 2, which is equals to 5, which is equation number 1. Similarly, by applying node analysis at node 2, v2 minus v1 by 3 plus v2 minus 0 by 5 plus v2 minus 10 by 4, which is equals to 0. See, for this 4 ohms resistor, one side voltage is v2, other side voltage is 10 volts. Here we are taking reference as node 2, that's why v2 minus 10 by 4. Here also by separating minus v1 by 3 plus v2 by 5 plus v2 by 4 minus 10 by 4 equals to 0. Separating v1 and v2 terms, minus v1 by 3 plus v2 into 1 by 3 plus 1 by 5 plus 1 by 4 equals to 10 by 4, which is equals to 2.5. This is equation number 2. By solving equations 1 and 2, we will get v1 is equals to 7.826 volts and v2 is equals to 6.521 volts. To find out the current supplied by the source, we need to find out the current flowing through the 2 ohms as well as current flowing through the 4 ohms. The current flowing through the 2 ohms is equals to 10 minus v1 by 2, which is equals to 10 minus 7.826 by 2, which is equals to 1.087 amperes. The current flowing through the 4 ohms is equals to 10 minus v2 by 4, which is equals to 10 minus 6.521 by 4, which will gives 0.869 amperes. Therefore, the supplied current equals to I 2 ohms as well as I 4 ohms, which is equals to 1.087 plus 0.869, which is equals to 1.956 amperes. 6. Using mesh analysis, find current flowing through 10 ohms resistor. In the given question, you need to find out the current flowing through the 10 ohms resistor. This is the branch, here is the 10 ohms resistor. By using mesh analysis, here we can observe there are 3 individual loops are there. First loop, second loop and third loop. In first loop, here we will assume a current I1 in the clockwise direction. At the same time, in the second loop we will assume a current I2 in clockwise direction, as well as in third loop also we will assume a current I3. Now here 3 individual loops are there, that's why we are assuming 3 individual currents: I1 current in the first loop, I2 current in the second loop, and I3 current in the third loop. Here, while applying KVL for first loop, here based on this direction we will place plus and minus inside the loop. For supply, already plus sign and minus sign is mentioned. Now here, by applying KVL for first loop, here we will write the algebraic sum of voltage equations. Algebraic sum of voltages in a closed loop, voltages and voltage drops in a closed loop is 0. Now here, if we start from 10 ohms, second sign is minus 10, I1 is the current flowing through 10 ohms, minus 20. Here for 20 ohms resistor, I1 current is flowing downward direction and I2 current is flowing upward direction. We are considered as the first loop is the reference, I1 minus I2 is the current flowing through the 20 ohm resistor. Second sign, we are following second sign, minus 40 plus 50 is equals to 0. By separating I1 and I2 terms, here is minus 10 I1, here is minus 20 into I1, therefore minus 30 I1 plus 20 I2 is equals to minus 10. This is equation number 1. Again, by applying KVL for second loop, for second loop also, inside loop we will consider plus sign and as well as minus sign based on the direction of current. Here direction is clockwise, that's why we are assuming plus sign and minus sign. We are writing plus sign and minus sign inside the loop. Minus 20 I2 minus 20 I2 minus I3. Since I2 current is flowing downward direction, whereas I3 current is flowing upward direction for this middle 20 ohms resistor, plus 40 minus 20 into I2 minus I1. Here this 20 ohm resistor is common between second loop as well as first loop. Again, by separating I1, I2 and I3 terms, we can write down the equation: 20 I1 minus 60 I2 plus 20 I3 is equals to minus 40. This is equation number 2. Similarly, we will write down the third loop equation. By applying KVL for third loop, here also we'll write based on the, we are assuming clockwise direction, plus sign and minus sign inside the loop. Minus 30 I3 minus 100 minus 20 into I3 minus I2 equals to 0. By separating I1 and I2 and I1, I2 and I3 terms, here there is no I1 term, only you have I2 and I3 terms. 20 I2 minus 50 I3 is equals to 100. By solving equations 1, 2 and 3, we can obtain the values of I1, I2 and I3. I1 is equals to 0.448 amperes, I2 is equals to 1.724 amperes and I3 is equals to minus 1.931 amperes. Here for I3 we are obtained minus sign, means the assumed direction is opposite to the actual current flow, and we are asked to find out the current flow through the 10 ohms resistor. The current flow in the 10 ohms resistor equals to I1, which is equals to 0.448 amperes. 7. Develop the relations to transform star to delta and delta to star connections. Basically, any three circuit elements, that is resistive, inductive or capacitive, may be connected in two different ways. One way of connecting these elements is called star connection or Y connection. The other way of connecting these elements is called delta connection. The circuit is said to be star connection if the three elements are shown as shown in figure A. When it appears like a star or inverted Y. Similarly, the circuit is said to be in delta connection if the three elements are connected as shown in figure B. When it appears like a delta, the above two circuits are equal if their respective resistance from the terminals AB, BC and CA are equal. Consider a star connected circuit as shown in figure A. The resistance from the terminals AB, BC and CA respectively are RAB in star is equals to RA plus RB, RBC in star is equals to RB plus RC, RCA in star is equals to RC plus RA. Similarly, in the delta connected network in the figure B, the resistance seen from the terminals AB, BC, CA respectively are RAB in delta is equals to R1 parallel to R2 plus R3, which is equals to R1 into R2 plus R3 by R1 plus R2 plus R3. RBC is equals to R3 parallel to R1 plus R2 equals to R3 into R1 plus R2 by R1 plus R2 plus R3. RCA in delta is equals to R2 parallel to R3, R2 parallel to R1 plus R3, R2 into R1 R plus R3 by R1 plus R2 plus R3. We evaluate the resistance between star and delta circuits. We get RA plus RB, RB plus RC and RC plus RA as shown in the equation 1 to 3. Subtracting equation 2 from equation 1 and adding to equation 3, we can find the RA equals to R1 R2 by R1 plus R2 plus R3. Similarly, RB and RC. Thus, a delta connection of R1, R2, R3 may be replaced by a star connection in resistors RA, RB, RC as determined from the equations 4, 5, 6. Now, if we multiply equations 4 and 5, 5 and 6, 6 and 4 and add these three, we get the final equation as under RA plus RARB R plus RBRC plus RCRA is equals to R1 square R2 R3 R3 square R1 R2 R2 square R1 R3 by R1 plus R2 plus R3 whole square. In equation 7, dividing the LHS by RA and gives R3, dividing it by RB gives R2 and doing the same with RC giving R1. Therefore, R1 equals to RA RB plus RB RC plus RC RA by RC. R2 equals to RA/RB plus RB/RC plus RC/RA by RB. R3 is equals to RA/RB plus RB/RC plus RC/RA by RA. From the above results, we can say that the star connected circuit can be transferred into delta connected circuit and vice versa. For the given network shown in figure, determine all branch currents and voltage across 6 ohm resistor using nodal analysis. The given question is, using nodal analysis you need to find out the current flowing through the each branch and the voltage across 6 ohm resistor. Now here we will assume first of all we will notice the nodes. Number of nodes are 3 nodes. Here node 1 at again node 2 and one more is a reference node. Here at node 1 we will assume a voltage V1 and at node 2 we will assume a voltage V2 and we will write down the, by applying node analysis we will write down the equations. Here V1 at node 1 and V2 at node 2. By applying node analysis, at node 1 V1 minus V2 by 8 plus V1 minus 0 by 10 minus 3 amperes is equals to 0. As the direction of current 3 amperes direction is upward direction, here we are considering as V1 as a reference. The direction from V1 is these three are the directions. The 3 amperes direction is opposite to the at node V1. If we take reference as a V1, the direction is exactly opposite to the 3 amperes. Hence we will consider a minus 3 amperes is equals to 0. By separating V1 and V2 terms, V1 into 1 by 8 plus 1 by 10 minus V2 by 8 is equals to 3. This is equation number 1. Again we will apply node analysis for node at node 2. By applying nodal analysis, at node 2 V2 minus V1 by 8. Since here we are taken reference is we are applying node analysis at node 2, that's why we are taken V2 minus V1 by 8 plus V2 minus 0 by 6 plus V2 minus 15 by 3 is equals to 0. Here also we will separate V1 and V2 terms. If you separate V1 and V2 terms, now for our convenience here I am writing minus V1 by 8 plus V2 into 1 by 8 plus 1 by 6 plus 1 by 3 is equals to 15 by 3. This is equation number 2. By solving equations 1 and 2, by solving equations 1 and 2, we will get V1 is equals to 20 volts and V2 is equals to 12 volts. We are asked to find out the current flowing through each element. The current flowing through the by observing here circuit, the current flowing through the 8 ohms is equals to V1 minus V2 by 8, and current flowing through the 10 ohms is V1 minus 0 by 10. The current flowing through the 6 ohms is V2 minus 0 by 6, and the current flowing through the 3 ohms is 15 minus V2 by 3 or V2 minus 15 by 3. Current flowing through the 8 ohms is equals to V1 minus V2 by 8, which is equals to 20 minus 12 by 8, which is 1 ampere. The current flowing through the 10 ohms is V1 by 10, which is equals to 20 by 10, which is 2 amperes, and current flowing through the 6 ohms is V2 by 6, which is 12 by 6 equals to 2 amperes, and current flowing through the 3 ohms V2 minus 15 by 3 or 15 minus V2 by 3, which is equals to 15 minus 12 by 3 is equals to 1 ampere, and the voltage across 6 ohms resistor is equals to V2 equals to 12 volts. See, for our convenience here, I suffix 8 means current flowing through the 8 ohms. I suffix 10 means current flowing through the 10 ohms. Find Vx for the circuit shown in figure. Here Vx is the voltage across this current source, which is the value of current source is Ix, which is unknown. Now in this problem here we know only the current flowing through the 8 ohms resistor, which is 5 amperes. Now here to solve this problem we need to apply KVL, KCL at the same time Ohm's law. Now by considering the given circuit, we can notice that here 8 ohms is the resistance value and 5 amperes is the current flowing through the 8 ohms resistor. Now from this we can directly find the value of voltage across this 8 ohms resistor, which is 5 amperes multiplied by 8, which is 40 volts. Here the direction of current, based on this direction we are placed this plus sign and minus sign. Here supply voltage is 60 volts and the 40 volts is the voltage drop across 8 ohms resistor. Now we already know that in a closed loop the sum of voltages in a closed loop is 0. Here 60 volts is the supply and the voltage drop here is 40 volts, and remaining 20 volts is the voltage drop which is appear across this 10 ohms resistor. And from this also we can we know that 20 volts is the voltage appear across this 10 ohms resistor and 10 ohms is the 20 volts is the voltage appear across this 10 ohms resistor, and from this we can able to find out the current, which is 20 by 10, which is equals to 2 amperes. Now if we apply KCL at this node, 22 amperes is the downward direction and 5 amperes is the, that is 2 amperes is the outgoing current and incoming current is 5 amperes. The sum of incoming current is equals to sum of outgoing current, or from the KCL algebraic sum of currents at a node is 0. Here we can able to find out the current flowing to the 4 ohm resistor, which is equals to 3 amperes. since 5 amperes is the incoming current and outgoing currents are 3 amperes, 3 plus 2 which is equals to 5 amperes. Now here we know that 3 amperes is the current flowing through the 4 ohm resistor. Therefore the voltage appear across this 4 ohm resistor is 3 multiplied by 4 which is 12 volts. Again here if you observe this loop, voltage sum of voltages in a closed loop is 0. Here is 20 volts, sum of 12 volts and 8 volts. Here 8 volts is the voltage appear across the 2 ohm resistor. Now from this Ohm's law, by applying Ohm's law, I equals to V by R. 8 by 2 will give us an 4 amperes is the current. 8 by 2 will give us a 4 amperes is the current flowing through the 4 ohm. Here 3 amperes is incoming and 4 amperes is the outgoing. Therefore the current flowing through the Ix, the current flowing from this branch which is equals to 1 ampere. Therefore the value of Ix equals to 1 ampere. At the same time, here if you observe at this node, let us assume this is at node 1, the voltage appear across 2 ohms is 8 ohms, which is the voltage V1 is equals to 8 volts, which are parallel to Vx. Therefore the value of Vx is equals to 8 volts and the value of Ix is equals to 1 ampere. Now while you are solving, you must have to draw the circuit for each and every step like this. You have to mention all the circuits. At each and every step you must have to draw the circuit. Now in the first case, now while you are applying KVL, now if you are applying the Ohm's law and if you are applying the KCL, now again you are applying Ohm's law and by applying KVL, thank you for watching. Please like, share and subscribe if you like.